I'm Mark O'Malley from Imperial College London. So just a few introductory remarks. So first of all, generally speaking, at a session like this, I generally sort of have a sort of an introductory joke to sort of, as an icebreaker. But unfortunately, all my jokes were stolen by Steve in the last. Is Steve here? Steve from Excel. So he stole my joke about AI. He stole my joke about the IRA, Irish Republican Army. He stole my joke about drinking sessions. I mean, he stole everything. He stole my joke about dress code. I put on long trousers. But on a serious matter, then I suppose I have to be serious. Steve did say one thing very interesting to me. He's a new board member of ESIG, and he sort of was saying that this meeting contrasts with many others that he goes to, which is true. But I think it contrasts not only in sort of the detail, but also in terms of the breadth, because the session before this was on integrated planning, which is a big picture stuff. And now we're about to get down into the weeds and oscillations. So I think that that's one of the really important things about ESIG is that it goes from sort of very big planning right down to some very detailed stuff. And that was discussed by myself and Nisha. Is she here? Anisha from CERC? Okay, she's not here. So just in terms of oscillation, so these are things that sort of, in this business, in my experience, what happens is that every now and again in this business, something pops up from down there in the weeds that causes real trouble for system operators. And this is definitely one of them. And I'll leave it to my colleagues to elaborate on that. This is an issue now for the system operators, so much so that in fact, tomorrow we're having a full day session on this. This is just a sort of a teaser session for 2 hours, but tomorrow we're having a whole day workshop on it. And if you're still interested in attending that, there is some places for that tomorrow. If you want to talk to Ryan Willis, you can. So my colleagues here will do some detail on this. So Nick, there's sort of there's 5 speakers, but they're in 3 lots. So Nick Miller is going to do a sort of I'll call it the introductory talk, and he's going to introduce this document, which is not in the public domain, but will be. It's an ESIG report that he'll talk about. Then 2 of the system operators, Xiaoyao and Yunzi, are going to speak from ERCOT and National Grid ESO's point of view, because they are really experiencing these things. And then Shahil and Vahan will deal with some of the solutions. So it's really introduction, the problem, and solution is the way it goes. So one thing I will say, though, to go back to the AI is not the solution to this. I'll just say that as I think it's worth saying that just in case, because everybody thinks AI is the solution to everything. Okay, so Nick, floor is yours. So I think everyone knows Nick Miller. Nick Miller.
There I am. How do I sound? All right, super. So yeah, AI probably isn't the answer, but I might be. He's a little intelligent. So I got to spend my allocation here to introduce you to a product of your participation in ESIG. So this is the first kind of cotillion for this document, I guess. So a few words here. Mark introduced the idea that the industry is excited, right? So there's this litany of oscillations starting to grow and show up with a variety of causality. And there's some things that are different, right? The behaviors are more driven by control and less by physics, less by impedances and inertias, and because their genesis looks a little different, or looks in many cases a lot different. This is new ground for us. One of the points here that sort of shows up and is important for this discussion is that this is new stuff on top of a system that's got a lot of existing things. So it's not just IBRs, it is systemic, and we know a bunch. But basically, the genesis of this guide is through GPST and ESIG of a sort of generic call for help. We've got oscillations. So the result of that, which is the subject here today, is this document, and I'm going to read the words of the title here. Diagnosis and mitigation of observed oscillations in IBR dominant power systems, a practical guide. So we got a room here of experts, people that have published and participated in IEEE documents and C-grade documents and lots of other stuff. And the the amount of material that is available is frankly overwhelming. And the intent of this guide is not to cover everything, but to be a place where the person holding the bag in operations in a utility that is faced with, we see oscillations. Go figure it out and figure out what to do about it. So that is the gestalt of this document. This isn't how do I understand all oscillations? How do I plan a system to avoid oscillations? All those things are adjacencies. This is, I see this, what the heck is it and what do I do about it? And that guides everything in here. And one of the things that's happened in this document is we tried very hard to emphasize the practical aspects. So this isn't everything. Mark held it up. I can hold my copy up again. It is simultaneously too short and too long. Okay. This is kind of everything you need to know about oscillations. Well, that's nonsense, right? There's tens of thousands of pages of material out there. But the poor person in the operations center that sees an oscillogram, we're not doing them any good by saying, here's the reference stack, knock yourself out, go fix the problem. So this is, we started this thing with the idea of what is it? Is this absolutely essential step on the road to how do you fix it? And the early versions of this slide that many of you have seen me talk about this thing, because it's been a journey of about 1.5 years, I used field guides to birds and had the imagery of oh, you know, what kind of bird is this? And you go through some sort of rigid hierarchy and out pops it's a scarlet tanager. That doesn't work. And as we worked on it from that angle, this is much more like medicine, much more like first aid. And indeed, I use the language of diagnostician throughout the document. I'm trying to figure out what the disease is. And this document is the field guide, right? From when you were a Boy or Girl Scout, you had the little guide. It's like, oh, maybe it's a dislocated shoulder and I'm 10 miles from the trailhead. What do I do about it? It's that sort of document with some more detail. It is absolutely not an in-depth scholarly document. And contributors like Shahil really got into it and wrote me very crisp, short sentences to capture things that sometimes might have taken a lot of space. So it's still, there's still a hierarchy. We adopted and adjusted from, so everybody should recognize this figure. I hope it's readable up there, but that's the IEEE stability space, right? That document has been enhanced in recent years to add converter-driven and resident stability, and it's kind of the whole world, and it's the gold standard of characterizing stability problems. But the reality is, as we started to work with that, found that in the narrow context of oscillations and in the narrow context of trying to figure out what it is, this hierarchy is actually quite difficult to work with because stuff leaps across from small signal and voltage and resonance. And it's like, which box are in? You try to force the diagnostics into that. It doesn't work very well. So we've got 5 major categories of diseases. And under those 5 diseases, there's a bunch of sub ones. So all of the subsequent material in it has got 15 kinds of ailments, or consult the experts because we don't know what the heck it is. And there's a fair amount of we don't know what the heck it is. This is trying to capture the existing thinking. So we introduce a process in the document that is in that spirit of diagnosis. So I've got some field measurements that show oscillations. If I've got good field measurements, I can probably believe that I've got oscillations. If I've got oscillations in a simulation, the very first thing you ask is, do you trust the simulation? Okay, not what do I do about it? Do you trust it? And then you go into a box, this initial assessment, and I got a bunch of tools. We've developed a bunch of tools to try to screen. What is it? Which one of these 15 diseases might it be, with the view of having 1 or 2 fall out of that process and go into a much deeper dive of diagnostics on what it might be. And in the process of the what it might be, also materialize what's the treatment for the disease, right? That doesn't really happen separately, but it's not identical process, right? figuring out what's wrong isn't exactly the same thing as figuring out how to fix it, but they're intertwined. So everything in the document is laid out with that philosophy. So this is a condensation. I guess it's a little bit of an eye chart. I was trying to not make it too bad of the table of contents. So there's a bunch of discussion about the language of oscillations, the fact that it's not uniform. People call different things, different stuff, the taxonomy, how to make good measurements, how to trust your measurements, how to make sure that the quality and the information that you're trying to make decisions on is good. How can you signal process? And then what is your initial guess at the ailment? That's what this next initial assessment. And then a whole bunch of gory details. There's a whole section written on latency, because latency ends up being a common thread in many of the ailments that show up. And then there's a whole bunch of things about how to avoid common simulation errors. Stuff where you simulate or perceive out of a simulation that you've got an oscillation problem when in fact it's the simulation's fault. Have you used the right tool? Right. So this initial simulation we have, so this is a one level down in flowcharts. There's lots of flowcharts or several flowcharts in the document. Screening questions. What does it look like? And this is very much written from the point of view of not exotica. If it walks like a duck and quacks like a duck, it's probably a duck. That's kind of woven through this document. We aren't looking for duck imposters. That's too sophisticated for this. All right. So do you trust? What's it look like? And there's a lot of help. And now it wouldn't be a presentation from Nick without at least one eyeball wrenching psychedelic thing here. So this is it. So this is a matrix of which I do not expect you to be able to read it, but across the top are my 15 diseases. And the vertical axis are characteristics, answers to questions. What does it look like? Does it quack? You know, and they're grouped together. And then the greens are, if you see this, that is an essential characteristic of this particular disease. Yellow is, yeah, that's like that is a possible indicator. Gray is I don't care. If I see orange up there, if I saw this, it's probably not that. And red is if I see this, it is absolutely not that disease. So a lot of thought went into this. It gets people crazy, right? Everybody's got their own opinion on what color they should be, and they yell at me. So, have some fun with that. And then we go into a process in the guide of okay, I got measurements. How do I suck information out of the measurements? How do I suck some information out of the signal? How do I plot it? How do I make sure it's not garbage? What kind of tests or diagnostic simulations do I need to go deeper into understanding that this guess that this is the disease is actually it? All right. And then you come along and you say, do I really trust that? If the answer is no, you go off somewhere that's out beyond the scope of this document. But if you think you figured it out, then the next question, and I got an earful of this from several of the people that are meant to be the audience for this, which is, do I really need to fix the problem? There's quite a bit of language in there about that. But the question is, if you have no idea at all what the oscillation is, what the causality is, to ignore it takes some stupidity, basically. But once you've figured out what it is, it may be a perfectly legitimate answer to say, screw it. This isn't important enough, or I can operate around it I don't need to fix it. So oscillations don't have to be fixed, but we make the argument that you better figure out what it is, right? Because little doesn't equal unimportant, for example, SSR, right? So that's the structure of this thing. I just put this as one example of a figure. There's a lot of language out there. People call different things. So there's figures to try to explain what we're talking about. So one of the sections is in a section called subsynchronous torsional interaction. And we made these cartoons. They kind of come in the traditional flavor of great big inverters like HVDC interacting with torsionals. And then we got a newer world of lots and lots of diverse inverters interacting, but the characteristic here is essential to be causing torsional interaction with synchronous machines. And other kinds of stuff are a different disease and have a somewhat different class of solutions. So it begs your question, right? You see that, you say, well, how do I get at that? So there's a long discussion in the document. It's actually not that long. There's brief discussion in the document of all the different flavor tools that can be brought to bear. And there's another one of those psychedelic charts. If this is your problem, this is the primary tool, this is the secondary tool. If this is your problem, if you've got SSTI, then you do not use fundamental frequency phasor analysis because it's garbage. So it's a red box, right? So those kinds of things. So there's a lot of discussion that was very emotional for some of these things. Some people think some methods that are talked about in the document are the cat's pajamas. Other people think the same method is pretty sketchy. Tried to be even-handed with that, so that's all built in. So to wrap me up, the document is in this pretty final stage. You, as an audience, are welcome to contact ESIG and get a copy of it and make comments over the next few weeks. We're going to take inputs from the workshop tomorrow. The thing's going to get cleaned up and then be released as a polished ESIG product open to the public. And a lot of people want to get hard copy of it. ESIG's going to have to figure out how to make hard copy. So we'll see how that works. Okay, I went over just ever so slightly.
Okay. Okay, thanks, Nick. So now Xiaoyao, so I suppose what Nick's trying to do is introduce the problem, but Xiaoyao is going to actually show you some of the real issues. Isn't that right, Xiaoyao?
Yeah, thank you. Yeah.
The real things.
Hi, good afternoon. Yeah, I'm Shahil. I'm coming from UK as a system operator. So my team has been heavily involved with looking at issues associated with renewable energy integration and operation. Some of the Pathfinder projects discussed a lot yesterday, so we've been heavily involved with that. If you do have some questions, feel free to come talk to me about Pathfinder as well. So today I just want to share some of the experience we got with GB system around the system oscillations. So a bit of background information about the GB system. So we have 3 TOs. We are the system operator. So we're currently part of the national grid and national grid electricity system operator. And we mainly operate the system, making sure it's secure and safe and economic and efficient as well. And currently, we are still part of the national grid group. But from July this year, we have become an independent system operator. We're going to split out from national grid and become publicly owned independent system operator. And by doing that, we're also taking some of the additional roles as well. So we're not only looking after electricity system, we'll be looking at the whole energy system planning, including gas, hydrogen, and some of the heat operation as well. So as the same to the trend to the wider world, I mean, we've been last 20 years, we've been through the journey about decarbonize our energy system. So we're starting to have more and more renewable generation coming to the system. We have retired some of the coal-fired power station. As you can see that we no longer have any coal-fired power station from 2025. And our offshore wind has been tremendous volume has been integrated into the system in the last 20 years. We're starting to see more and more PV system connecting to the system as well, and also storage. So when we're looking at what we actually have achieved in 2023, we probably around January time, we have 91% of the zero carbon in the system. And instantaneously, a penetration level of IBR we achieved about 75% as well in last year. So for our goal is by 2025, we should be able to operate the system with 100% zero carbon operation for a very short period of time. But we like to continue to do that. By 2035, we should be able to operate the system all the time with zero carbon operation generation. So just a little bit around oscillation. So oscillation is not something unfamiliar to us. And so even in the past, when we have a system with a synchronous machine dominated, we have an oscillation in the system, but that's mainly in the form of the low frequency oscillation. And that's inter-area from Scotland and England, Wales. We have some oscillation in there. And we also have some localized issue that if some of the synchronous machines, the AVR and the PSS that haven't been tuned properly, that would have some local oscillation going on as well. And as we put in some of the series compensation between Scotland and England Wales, so we're starting to have to consider the SSTI type of issue as well. That's the reason we're actually putting a series controlled series compensation rather than a pure compensation, just try to mitigate those issues. And so as more and more IBR connecting system, we're starting to see the oscillation, the pattern changes a bit. I mean, so some of the things happened in 2021. I think probably we presented in a couple of years ago in here. So we're starting to see 8 Hz oscillation happen in the system. There's no obvious trigger in that. And for this particular event, so it lasts about 20 to 30 seconds, and it's about 30 minutes apart as well. And this is the first time happened in our system. So we did a lot of simulation studies and making sure we understand it. And in the end, some of the HVD's control system has been modified to making sure that this problem can will be addressed or has been addressed. So since that, we haven't had a lot of the oscillation in that area until that 2023, which is last year, summertime. I have to say that within that area, we have a huge amount of the IBR concentration in that area. We only have a very limited amount of the hydro plant, which is the synchronous machine in that area. And since 2021, there's additional IBRs or offshore wind has been coming to that area as well, so making that overall system more IBR dominated. So around 2023, summertime from June to July, that we had about 5 events of the subsynchronous oscillation in the system. So the frequency is around 5 to 10 Hertz. I mean, I think the shortest the event lasts about 1 or 2 seconds, but longest lasts about 5 minutes. So it's causing quite a significant impact to the system. So we have some generation tripping, we have interconnector tripping as well. So I'm just going to go through a little bit more detail in there. As I said, June or July time, oscillation, 5 to 10 Hertz, lasting from 1 second to 5 seconds, and causing the tripping of generation, synchronous machine, interconnector, and some offshore, or some of the wind tripping as well. So as an ESO, during the time, we've been taking some defensive measure to making sure we can still safely operate the system. And during the same time, we've been working with industry to set up a team together to investigate the root cause of the issue. And we found out the most likely case, the reason for the oscillation around middle of the July, and we're starting to retune some of the control system of the user's plan, and that around the middle of August time that the new settings had been implemented into the system, and since then we haven't seen any sort of undamped oscillation after that. So the defensive measure we put in place is mainly just around 2 areas. One is how we actually reduce the likelihood of the SSO occurring. That's in the sense is that we try to synchronize more traditional generation into the system. In this particular case, is around hydro in the system. And we try to making system topology stronger. So that means that we have to cancel some of the outages, making sure the system closely linked together. And we try to increase some of inertia as well within that particular area to making sure that the system is stronger as well. And apart from that, we also do another set of work we're doing, just try to manage the impact of the subsynchronous oscillation as well. So if there's a risk of the subsynchronous oscillation that could lead a trip of the generation, this means that we have to hold additional response and reserve if the worst things does happen, at least we have enough response and reserve in there to making sure system frequency is still okay. So how it was resolved, that's probably the most interesting slide. I'm going to spend a little bit more time to talk about, Amy. So during the event, what the information we have is that we have the PMU information, we have all the generation running patterns, we have the system topology, and we might have some user data as well. So we're gonna have to figure out what exactly is the cause of the problem. So it's the different work stream has been established to try to look into that issue. So one is just try to correlate all this event. Is there anything in common? Can we actually find out any patterns from those events? Is there any particular generation has been behaved strangely, or is there any sort of topology causing the problem? So we've been spending quite a lot of time to investigate that, but unfortunately, there's no straight correlations. So we couldn't find any correlation in terms of the inertia level, in terms of the flow level, in terms of the wind output, in that just in terms of topology. Now there's no correlation on that one. So another approach we try to do is that we try to run the EMT simulation as well, but that seems to be taking very long time for the EMT simulation to give us the convincing result to say what's the exact reason of the oscillation. So we have to rely on the PMU data to try to find out what's the cause of the oscillation. So the approach we're taking is that we mainly use the two methods. One is that we're using the dissipating energy flow. So we feeding the PMU information into the DEF tools it's currently provided by the New England ISO. We try to using those tools to determine that which area we should be focused on. Our experience on the DEF is that it not always gives you the consistent result, but it can actually highlight some of the areas you should be focused on. So that's our main sort of approach. We're using tools, using it as a screening tools to determine that which area you should be putting your effort into that. And another part is that once we identify those areas, so we're extending to look into the detail of the PMU information. The key information we actually used is around P and Q and the terminal voltage of the generator. What we tend to look at is that we align all the generation in that area together, and we're starting to looking at during the oscillation, is that any output of the generator looks a bit strange to compare to other generator. So by doing that, we also identify that if one of the generator has been singled out, then we're starting to looking at the relationship, let's say voltage and reactive power relationship to see that whether that's what we expected or not. So by doing all this step by step, we managed to narrow the problem down into a particular user group. So we've been then we went had a discussion with all this user group to say, okay, what can we do? To eliminate this type of issue, because that our study or the data shows that you could be you could at least amplify the oscillation. It's difficult to say whether you're causing the oscillation or not, but at least that by the looks of it, you are actually making the oscillation a bit worse. So we're starting to we defined a set of the simulation tests that the user have to do. That mainly around you have to force the oscillation into the user's system model. Then starting to see the response of the user's plan to say whether that to amplify or actually that to damp the oscillation. So by doing that, we can clearly see some of the users' plan amplify the oscillation. So that's after that, then we just taking them offline and we ask them to fix the problem. So we work together with the OEM, come up with a new set of the control parameters. And in the end, the simulation at least demonstrates there's a good damping improvement by adopting those new parameters. Then after that, we had a phased return of those services. So once they implemented the control system change, that 25% of the output initially being kept, operate for a couple of weeks, nothing happened, then they move to 50%, then in the end, that's moved to the 100%. So I'm quite happy to say that after that, there seems that there's no undamped oscillation in there. So very quickly, investigation, the conclusion is that with the data, we haven't found any sort of linkage with some of the traditionally people thinking that the low short circuit level or the low inertia, we couldn't find any sort of clear correlation with that. And we kind of identify the issue and fix the problem together with the users. And there's also some additional work has been identified that what we actually need to do to improve how we actually managing this type of event in the system. That's mainly around real-time monitoring, and how do we actually come up with a good real-time monitoring system so that we know that also how to take actions, and review the compliance process. Although we did some work with our particular users, but we want that that process to be adopted for the future generation as well. And the third one is that we have to improve the EMT modeling, but that's more around a longer term type of approach. So if I may take 1 more minute, let me just quickly show some of the things we implemented after our oscillation event. So this is a oscillation monitoring system we implemented in our GP system as work together with reactive technology on that. So what the system does is that it continuously calculating a damping factor of the particular voltage around the key voltage measurement in the system. What is interesting is that you try to find out the pattern. That's for this particular graph I try to show you. When you're looking at the green box, we can clearly see there's a sustained damping factor change at a particular time. Based on that information, what we try to do, we try to correlate that back to the either will be system configuration change or either be generation pattern change. So that gives us the confidence with to say some of the event might be helping us, or some of the actions might not, because it makes things worse. So at least that by doing that, what we try to do is that try to establish if we are going to have this problem in the future, at least we need a list of the actions we think that's going to be effective. And that's one of the good way to measure that. And another thing is that around compliance process. And so as I mentioned before, that a set of you asked them to do a new set of the study to demonstrate the improved damping performance. And we captured that and we published a guidance note called System Oscillation Assessment for IPRs. So that any of the new users come to the system need to go through that all this EMT testing to making sure they can demonstrate a good damping performance before they come in connecting to the system. So that's there's a link there that you guys can feel free to have a read. And the third one is probably EMT improvement. So that's going to be taking very long time. As one key change that we try to do is that so currently there's in GB there's a requirement for any of the generator connecting after 2022 have to provide a EMT model to us. So we'd like to introduce a new gray code modification to apply that retrospectively. So any of the existing generation in the system, if it's requested by the system operator, have to provide EMT model as well. And another thing is that we like to create a platform for the EMT simulation portal. So any of the new user, if they want to look into the interaction with the rest of the system, we like to have this portal ready, then they can just connecting their user model into that portal as a part of the control interaction assessment. So that's our experience. Hopefully that will be some interesting question. Thank you.
Okay, thanks, Xiaoyao. So now we move to ERCOT and to Yunzi. And I mean, it was mentioned there before, this is the GPST. I mean, these are all members of the GPST, and there is a reason these 6 system operators are in the GPST, because they are, I'm not saying they're in it because they're all experiencing this. They're in this because they have very high penetrations. Ergo, they're all experiencing this to some extent. Okay.
Thank you, Mark. Can you hear me? Okay, thank you. Good afternoon. My name is Yunzi Cheng. I'm from ERCOT Operations DPD Analysis. I'm going to talk about the system oscillations or subsystem oscillation or SSOs in ERCOT system. But before that, I'd like to talk about some activities in the RBR SSO task force, which I initiated in 2017 with Professor Lin Fan. So this is the web page of this task force. We initially set up this task force for wind SSO, because at the time, most of the SSO events are with wind farms. And in 2021, we renamed this task force to RBR SSO because we found more SSO events with solar projects as well. And as you can see from this page, we have a lot of activities and also documents available in this website. Especially we have multiple task force meetings and also panel sessions. For example, Shahil was part of the panel session to talk about his brilliant frequency scan tools. So we have a lot of material here. And in particular, I like to talk about two documents. One is a task force report that we published in 2020. It is available in Operability website. You can download for free if you have Operability membership. And the second one is a paper that we recently published in Operability transactional power system. It's a real world SSO event in power grid with a high penetration of RBRs. We basically summarize the recent 19 RBR SSO events. We also investigate their mechanism. Also, we try to categorize those events based on their mechanism. Basically, there are kind of two types of this RBR SSOs. One is related to the service compensation and type 3 wind farm. This one is kind of well understood and studied. However, I don't think the problem has been solved. We still have some challenge. We still have some events for this one. And second category is a high penetration of RBR in weak grid condition without synchronous capacitor. A typical example is 2015 North China SSO event. And this is ongoing effort. It's pretty complicated. There are still a lot of research and also industry engineers work on this one. As you can see, we have more and more this kind of events happen in recent years. So that's about the task force. And this list basically is some reported IBR SSO events from the world. If we have event in US, China, Canada, Australia, and Great British, and the frequency ranges between 3 to 34 Hertz, typical SSO frequency. And the mechanism is basically either a type 3 wind turbine under series capacitor or the RBRs under weak grid condition like a solar or offshore wind or type 4 wind and weak grid condition. So that's about this task force. You know, sometimes I think I probably or we did not really do a good job. Otherwise, we don't need this meeting today. Now I like to talk about ERCOT. You probably know we have East connection, Western connection, and ERCOT interconnection. We don't have any AC line connected to outside. We have a few DC lines, but the total capacity is very small compared to our peak load. Some quick facts. We have a lot of renewables. For wind, we have more than 38 gigawatt of wind capacity. As Prabhu mentioned this morning, we are probably the #1 in US. And the highest wind penetration is close to 70%. And we have 22 gigawatts solar installed, and the penetration record is close to 40%. And this one shows the wind addition by year. As you can see, the wind grew pretty fast, but recently kind of slowed down. Right now we have 38 gigawatt, and in the near future we'll probably have 40 gigawatt wind, and solar pretty fast and still growing pretty fast. Now we have 22 gigawatt. In the near future we will have probably 50 gigawatt, and then same thing for the battery. 5 gigawatt battery, and near future will be close to 20 gigawatt. So together we have 40 gigawatt of wind, 50 gigawatt solar, and 20 gigawatt battery. Together it will be 110 gigawatt in the near future. So it's kind of huge, considering our peak load is only 85 gigawatt, and we pretty much isolated from other grid. SSO events, we have very great related SSO event in 2015. It's a type 4 wind farm connected to 69 kV. During the event, we have a line from bus 5 to bus 6 tripped. So the source signal ratio dropped to 2. And then we have undamped oscillation, 4 Hz oscillation. And then we were able to replicate that one. And we also find out if we can tune the control of the wind, or if we can increase the system strength, then this problem can be solved. And to deal with this kind of weak grid SSO, we basically create a system strength test requirement as part of a model quality test. And the minimum source signal requirement is 1.5. And for your information, we have model quality test requirement for PSE and also PSCAD. And we also publish 2 tools. One is the DMView for PSE, PMView for PSCAD. Those are free and it's on the Google website, you can download. We also thinking about like how to deal with weak grid condition, right? So at one side, we try to increase the system strength. So one natural way is to add synchronous condensers. So last year, we proposed 6 additional synchronous condensers in West Texas, which is great with great area with a lot of RBRs, like 40 gigawatt RBR in West Texas. And those projects have been approved by PUC and will be serviced in 2027. And now the series capacitor released SSO. This is a major SSO event or major SSO concern in ERCOT. It is because we have many series capacitors. As you can see here, we have in total 18 series capacitors on 340 kV lines, especially the 4 capacitors in South Texas, which cause a lot of SSR issues and events. This is the pretty famous event in 2009, the first event related to series compensation and type 3 wind farms. So we had a fault that tripped the line between Aho to Long Hill. Then all the wind farm at Aho station became radially connected to the real Hondo series capacitor. And all the wind farm here are defect machines. So we have very high current and result into damage to the both series compensation and the wind turbine generators. This is really a famous event, and this one is really triggered the study from the industry and also from academia side. To deal with that one, we propose some study framework. It is 3-step study framework for series compensation related to SSO. The first step is the topology screening. Basically, we try to count how many contingency that will need the radio connection between the series compensation and the RBRs, which is very key condition. Radio connection between the RBRs, or this case is type 3 wind farms and the series compensation. If the number of contingency is very small, then that means high risk. So we will perform the frequency scan or impedance scan. And then if the impedance scan indicate issues, then we will go to the 3rd step, which is EMT analysis or PSCAD simulation to accurately capture the SSO risk. I'm not going to the details, but here is an example. So we have an impedance scan or frequency scan from the wind farm side. Then we have the system side frequency scan, and then we add them together to have a total impedance, the reactance and the resistance. The reactance is basically the red curve, the resistance is the blue curve, and then we look at the crossover. We look at reactance crossover from negative to positive. In this case, the red curve cross from negative to positive at 8 to 9 Hertz. And more important, at that frequency, the resistance, the negative curve is negative. That means SSO risk or SSR risk at 8 to 9 Hertz. And then we perform the PSCAD simulation. Not only the PSCAD simulation verify that risk of SSO, and also the FFT analysis indicate the frequency is really 9 Hertz, which match with the frequency scan pretty good. From now, look like everything is perfect until we have 3 SSO event happen again in South Texas in 2017. And all the events are related to the defect machines radially connect to the series compensation. Basically, we have 3 events. Each event, like you have a wind farms series connect to the series compensation, and we have damped or undamped oscillation. The frequency is about 20 to 30 hertz, and the wind farm were tripped during the undamped events. So basically, there's no damage for the devices, unlike 2009. But it's still it's not good because those projects they have studied SSR and they identify no issues at the time, but in reality it happened. I think we work with the vendors, try to tune their control to solve the issues, but unfortunately last year it happened again. In this one we have a station 4 to station 5, that line got tripped, and then we have 5 wind farm became radially connected to the series compensation. And this time it's more complicated because those 5 wind farms, some are defect machines, some are type 4 machines. But still, the SSO happened, and also the series capacitor automatically bypassed because of the protection. So no damage, and 1 wind farm tripped. So as I said, this mechanism has been very understood and studied, but still it's kind of a challenge for the SSO mitigation control. I think because the reason is probably it's hard to design a controller that can work under different operation conditions, especially you have multiple projects from different vendors or even different technology. So it's very challenging to make sure this mitigation always control. So that is this SSO event. In summary, we have weak-grade SSO concerns, and we have the system strength test as a requirement. And also we may curtail those projects based on SCR or based on the dynamic simulation. And then on one side, we try to add syncons to increase system strength. I think on the other side, the RBR side, probably some more advanced control can be used, such as reforming controls. I remember Shahil showing his frequency scan, there's reforming show a positive sequence, a positive damping across subsequent frequency range. It probably will help that situation as well. And then as a series compensation related to SL side, I think the message is really the tuning of the control is very complex. It may or may not work. So our suggestion is really to avoid the radio connection between the RBRs and series compensation under normal condition and also the critical contingencies. Besides, try to avoid direct connection of RBR to series capacitors. That's all for my presentation. I have a few reference papers here just for your reference. Thank you.
Okay, so we'll have our next speaker, and I just would note on the last slide the word curtailment was in there, and I think that's something we'll have to elaborate on. That it would appear that the solution is curtailment, but that's not a long-term solution. So I think that's one of the things we have to discuss. Okay, so Shahil is from NREL. Away you go, Shahil.
Yeah, thanks, Mark. Hello, everyone. My name is Shahil Shah. I'm a researcher at National Renewable Energy Laboratory. I'm going to provide an update on collaboration that we are doing with Australian energy market operator or system operator in Australia about understanding the root cause of oscillations that they have been seeing over the last few years using impedance-based analysis methods. So here is the outline that I'm going to talk about. I'm going to talk about overview of the oscillations that have happened in Australia, the grid impedance PN tool that we have developed at NREL, how we are using it for understanding root cause of oscillations in Australia, a couple of different steps using IBR impedance scan in SMEP format, as well as doing the impedance scan using the entire network model with a bunch of IBRs and then summary of the results. So AEMO has been seeing this 17 to 20 hertz oscillations over the last 3 to 4 years. They have taken some mitigation measures which have reduced the frequency at which, or basically the regularity at which they are seeing this problem. But it's been going on. And the question is who is triggering these oscillations? So before they started working with us, and their previous finding based on the report that came out in February last year was that here is a map of Victoria and New South Wales states in Australia where they are seeing these oscillations. So if you can, not sure if you're able to see my cursor, yes. So what they found out based on the measurement that the oscillations were mostly on the left side or the western part of this map. Also, the oscillations were not there when one of the line over here, basically here was tripped. So sorry, the oscillations were there even when the line was tripped. And also the other finding was that oscillation were there when in one of the event when this line was tripped. So basically what it means is that oscillations are coming out from this region. And this is what they found out based on the measurements and then some of the tools that they used, which just looks at the measurement. And following Nick's analogy about diagnostics, what they really did was use stethoscope to identify where is the problem by looking at the measurement. And with stethoscope, if there's a problem in heart, you will hear it only when there's a problem, not only when you have measurements on when there's a problem, but not really the source of the problem. Now, you can have some more advanced tools using based on measurements of oscillations and do an EKG, right? But that will only tell you probably it will narrow down the problem, as I think Xiaoyao was also talking about, that you can, with certain of these tools, you can find out, okay, the problem is located in this region. But if you really want to understand the root cause of this problem, what you really need is an MRI scan. And that is what we have been developing at NREL. So we call it grid impedance scan tool. What it does is that the GIST block that you are seeing in the power in this map is basically a core piece of this tool, and we insert this GIST block between an IBR and rest of the power system in an EMT model, for example, PSCAD, and then GIST automatically scans the impedance of both the IBR and rest of the network, and that way it determines how this particular IBR is impacting the frequency and damping of various oscillation modes, whether it is contributing positive damping or negative damping, and if it is shifting the frequency of that mode. So basically we can find out the stability impact on IBR. Now we repeat this process at other IBRs, as many IBRs as you like, in a sequential manner. So it's a scalable tool. Like you, of course, it takes time to do this analysis, but we basically analyze impact of one IBR at a time, and then that gives you the full picture of stability. This is how the GIST looks like. So as I was mentioning, that we insert this GIST block between IBR and rest of the system in a whole system-wide PSCAD model. Then we do the impedance scan, basically for both the grid as well as the IBR, and this is done in an automated manner. And then finally, we do the stability analysis using this interface. So you get a basically full picture. And I'm going to walk you through some results about this on what is the workflow. So there are three major steps. The first step is identify IBRs and operating conditions that are suspected to have significant role in oscillations. So this is done based on measurement. You find out, okay, these IBRs are seeing a very high oscillation, so probably they have some role to play. You figure out that oscillation events have happened for this topology or this or that operating condition. So you narrow down the operating conditions, topology, and number of IBRs, which you suspect have a major role in these oscillations that you're seeing. Because doing the impedance scan analysis takes a lot of time. So once you have done that, then you go to step 2. For each IBR that has been shortlisted as a potential culprit in these oscillations, you perform impedance scan in SME format. SME means single machine infinite bus. So you connect that IBR model with an infinite bus voltage source and find out what is the impedance of IBR. And that really tells you if there are any internal oscillation modes in the system or not. And also if that IBR has any problem working with any type of weak grid or any series compensation. And once you have done impedance scan, you find out under which grid short circuit ratio or series compensation it will become unstable in just a couple of seconds, because you don't have to run any EMT simulations. You already have the impedance scan data. And once you have gone through that step 2, we go to step 3, because In step 2, you're looking at IBR separately in a single machine infinite bus format. In step 3, we do wide area scan. So we look at the whole, the impedance scan of the entire grid, provided that you have an accurate system-wide EMT simulation model. And that tells you how the IBRs in proximity are interacting with this particular IBR. And then we repeat the step as other IBRs as required. So this is an impedance scan at one particular IBR for operating condition 1. I don't expect you to like read these plots and understand like what is the stability characteristic of this IBR, but these are 2x2 sequence admittance matrices on the left, and then on the right it's a DQ admittance. We can use this impedance matrix or impedance scan to figure out under what conditions this IBR will become unstable in terms of short circuit ratio of the grid. So we figured that based on this impedance scan, the IBR was fine. It didn't have any stability issue. For the same IBR, for a different operating condition, we call operating condition 2 here, this IBR has a severe resonance mode, and that you can see over here, like in the sequence admittance or even in the DQ admittance, and that is around 17 Hertz. And once we use that impedance scan and do Nyquist plot, basically stability analysis, we really figure out, okay, this IBR, whenever it operates at weak grid with short circuit ratio less than 3, it will become unstable. So great, right? We found a solution? No, not really, because this IBR will become unstable only when short circuit ratio is 2 or when the grid is extremely weak. But this short circuit ratio for that particular IBR, when this oscillation happened, was significantly higher than 2. And that was based on AEMO's analysis for using the positive sequence model, make sure what is the SCR ratio at different points. And there was no weak grid issue in the system. Then why they saw this oscillation? And to understand that, we go one step beyond, which is the third step. And we do a system scan. Yeah, this is just the summary of what I just said, that some IBRs in the system had a underdamped mode at 17 Hertz. That mode becomes unstable when the SCR is low. But the SMEEP analysis models grid as a simple RL branch. It doesn't look at the whole network. It doesn't look at the IBRs which are in proximity. So it doesn't reveal complex interactions among IBRs. So we go to step 3 and look at the impedance of the grid using the EMT model. And what you see on the screen is basically the positive sequence impedance scan of grid as seen by the IBR that we just looked previously. So this is the impedance scan of West Murray Zone grid. West Murray Zone is a balancing area in AEMO's territory. So the same grid looks quite different when other IBRs in the proximity of IBR1 are having a different operating conditions or dispatch conditions. So a black trace, which is just behind the red, you probably don't see that, is when the IBR2 and IBR3 are disabled. The red trace is when the IBR2 and 3 are enabled, but they're operating at the low risk condition where you didn't have that 17 Hertz resonance mode. And it is directly on top of the black one. So it's not changing the grid. But once IBR2, the blue trace, once IBR2 operates at high risk condition and IBR3 is still disabled, we start seeing this development of a resonance mode at around 73 Hertz. And which is basically, this is a positive sequence impedance. So 73 Hertz in the phase domain or phasor domain will translate to 23 Hertz, 50 Hertz being the fundamental frequency for Australia. So, and now when both IBR2 and 3 are operating at a high risk condition, the resonance becomes very severe, as you can see here. So what is really happening is that for IBR1, it has an internal resonance mode, which becomes unstable at the weak grid, but short circuit ratio is not really revealing that weak grid condition that is evolving whenever IBR2 and 3 go into their high risk mode. And that is why we are seeing this oscillations. And if I plot some other types of plots, like what we call model impedance plot, so the circles are really the mode of the grid in the absence of IBR1. And then when we connect IBR1, we see the unstable mode. And also from the Nyquist plot, we see the encirclement. In a nutshell, what this is showing is that IBR1 is causing that instability, but IBR2 and 3 have some role in it because they are creating an artificial weak grid condition. And this is how what you can do is you can quantify, for example, by looking at these plots, what is the damping without IBR1 and with IBR1, how much damping IBR1 is contributing. Basically, in this case, it is contributing, let's say, minus 15%. So it's reducing damping of that mode by 15%. Now you repeat this analysis at sequential other IBRs and then form a ranking table. Okay, IBR1 is contributing this much negative damping, IBR2 is contributing this much, IBR3 is perhaps contributing positive damping. And that will give you a full picture of like, what is the role of each IBR in this oscillation mode. So to summarize, impedance-based analysis provides a systematic solution to understand the root cause of power system oscillations. We are right now depending on highly accurate black box EMT models. The model that we use for doing the scan of Australian grid was provided by AEMO. It had around 45 IBR models, and there is a computational cost to doing impedance scan. Right now, for scanning an IBR, it takes us a couple of hours, but for scanning the grid of the entire Australia with this big model with 45 IBR black box models, it takes a couple of days to do one scan. So that's why we have to limit. We can't do this type of scans like for as many scenarios we may like. We are right now working on making our tool more faster by taking various sophisticated approaches so that we can reduce this time by an order of magnitude. The second thing we are doing with Australia is to try to understand if we can put a grid forming inverter or a synchronous condenser in that region and change the grid impedance characteristics and avoid that formation of the resonance mode. And another message is, as you have just seen, this use of short circuit ratio might result in over-optimistic estimation of grid strength, because sometimes you might think that the grid short circuit ratio is high enough, but because of complex controlled interactions among IBRs, the grid might be weak at certain frequencies. And that's why we need to use this more advanced tools to understand stability of power systems with higher amount of IBRs. That's it from me. Thank you.
Okay, thank you. Okay, I'm sure you're all getting your questions ready. I certainly am. So our last speaker is Vahan from NREL as well.
Yeah, okay. Hi.
Okay, Vahan.
Thank you, Mark, and good afternoon, everyone. I'd like to thank, as always, ESIC, Charlie, and everyone in ESIC for inviting us to be part of this workshop and allowing us to share the results of our research. And today I'll be sharing the results of our recent work that is related to the testing and demonstration at NREL test facilities on how IBRs can provide stability services in a grid. So with the result of research of a large NREL team, some key members of the team are shown here on this slide. So what is the motivation? I mean, nothing to add to previous speakers. It's an ongoing, oscillations are ongoing problem in any power system in the world. The stability services traditionally have been provided by synchronous machines using the power system stabilizer, PSS controls, which has been a very efficient and a cost-effective way of doing it. But since the paradigms is shifting, the synchronous machines are retiring and we're retiring more. The system characteristics are changing. The expectation is that IBRs should be part of stability provision schemes. The landscape is changing now specifically for battery systems because it's easier to do it with the batteries, and it's happening in many places in the world, including US. Lots of battery systems in California providing different type of grid support. But when it comes to wind and solar, that type of service is literally non-existent. Despite of many demonstrations NREL and others did in the past, and we showed that renewables can provide also essential reliability services have been proven and demonstrated, but even that hasn't been largely adopted in a grid. In this lower graph, we show the results of the frequency drift test on a 300 megawatt PV plant that we conducted in collaboration with the First Solar in California. So you can see is a textbook droop response, very linear. There's just nothing that can be achieved using synchronous machines. But nevertheless, this control is available, but is not by the industry. The focus of this presentation is mainly on the inter-area and the local modes, and that's also existing problem in many places in the US and in Europe. Large modes exist in the Western interconnection. We just learned about the same thing in ERCOT. Large across the Europe mode exists in Europe, all the way from Spain to Turkey. And the damping of those oscillations is also a big research effort in Europe. So on this slide, we show some examples of measured local mode oscillations in Colorado as we measure at NREL on a real grid. So NREL IBR stability control strategies can be enabled and used. And the goal of our work is to demonstrate that is possible. And also the ongoing improvements and advances in the wide area measurement systems and wide area damping control type of systems that goes along with the progress in the PMU based measurement and controls, especially the work done by the NASPINet, the new technologies being involved in a market, including multicast, PMU type of technologies, and also improvements in the cybersecurity make it possible also to use IBRs as part of wide area stability controls. So what we do in this area is mainly funded by US Department of Energy, by all ERE programs, wind, solar, water power, hydrogen fuel technology office, and also the Office of Electricity. So how we do this testing and demonstration? We do it at our test site called Flatiron's campus, which has utility scale wind turbines, utility scale PV, utility scale battery systems. We have multi-megawatt grid simulator. It's hard to see things on this scale, but it's not a multi-hundred megawatt system like a real power grid, but at least it's a scale that matters, that allows us to demonstrate this type of controls with the real hardware and with the real controllers. So we did a number of tests trying to characterize the frequency response of different IBR technologies. In this case, we show how the battery PV plant and the wind power plant respond to a set point, which is basically a sinusoid. And this way we're measuring the frequency response of a device, trying to understand the bandwidth in which it can provide damping services. So, and this is an end-to-end test. This is not just a wind turbine or a battery or PV. It's a wind turbine with its own controller coupled with the plant controller, although it's a wind power plant of one, for example, but it's really end-to-end test. So it characterizes the performance of a whole system. So we have been able to run many tests and characterize this frequency response of these devices, which has been published in the previous work, so I'm not going to repeat it. We also did this test. The advantage of our site that we are also coupled to a real variability of a resource that allows us to do a test for extended periods of time, like is shown in here for a single wind turbine, and then use the data to aggregate these measured results in a response of a larger wind plant. For example, after running in long time after different wind speed conditions and the power levels, we aggregated the output of a single wind turbine as a output of a large 250 megawatt wind power plant, and you can see that the output of a plant is essentially perfect textbook sine wave, of course with some time delay, which is a response time of the overall plant. So it basically shows that with the proper delay compensation, IBRs can be used to provide damping services. Oops, sorry. I'm going in the wrong direction. Yeah. Another advantage of IBRs is a totally independent control of active and reactive power. Some people may think this is a sinusoid that we generated just to show here, but no, this is a real, again, measurement on a 1.5 megawatt wind turbine. We show totally independent control of active and reactive power. We modulate them at the two different frequencies, and you can see that turbine responds perfectly. At some point there in the middle, the power changes, but its turbine is still able to maintain this type of response, and the reactive power response doesn't change at all. So that basically tells you that different types of control scheme, including the damping services related to active power control or reactive power control, or both at the same time, are possible as well. So another test apparatus that we use for this type of research is our multi-megawatt grid simulator. My colleague Shahil showed these slides yesterday, and I'll try to explain them from slightly different angle. These are multi-megawatt power electronic grid simulators that are voltage source converters, probably most powerful and capable voltage source or grid forming converters in the world, but nevertheless, we use them as a test apparatus. They have pretty fast bandwidth. This is our first 7 megawatt unit that has a 1 millisecond response time. So with this, we can emulate any desired type of grid conditions, both oscillatory behavior and also things like faults, emulation of stronger and weaker grids. The recent addition is a 20 megawatt simulator, which has been commissioned several months ago, and now it's actively used in all types of testing. So it is a more powerful device, but we learned some lessons and make it also much faster. So response time is 100 microseconds. So both devices are power hardware in a loop capable. So it allows to do very advanced testing when power hardware in a loop makes sense, of course, and demonstrate different type of controls and validate the models by renewables. But what makes it really valuable when you combine them in a setup like this? So this is a real existing setup or a platform that we already use, and I'll report some results that we achieved on this one. So now we are able to do multi-point of interconnection type of system emulation, which is represented by, in this case, by the Condor two-area system model. Everyone is using it to understand the physics and mitigation in inter-area oscillations. And we like to use it here too, because then we can compare with the non-real-time simulation, compare with others, results by others. So what is real in this system is the all renewable generation, wind, solar, battery, PV, synchronous condenser. What is also real is the PMU unit, the controllers of these plants, the central area controller, and also these devices are seeing a real voltage and real frequency and phase angle as it's happening on the terminals or on a particular buses of this power system. So what is virtual is essentially just the transmission lines and the models of synchronous generators, which is a very well-known science. We know well how to model. So things that matter, including the communications and delays and everything, are implemented here in a real hardware. So this is a really good platform to understand how you can control renewables to provide damping services, and what is the impact of the communications, especially the latencies, and how they can be compensated. So, as I said, the classic oscillation damping control is done by PSS, which this is a typical schematic, which we totally enabled in this system. So we only are using only controls provided by IBRs in this case. So we have two different IBRs on two different parts of a system. It can be represented by wind, solar, battery, and other combinations. We have the central controller, and we have also local controllers. So different scenarios can be tested to understand the advantages and disadvantages of a local and wide area control. We are also emulating all possible types of the delays that may exist in a real communication network. That is the data we learn from NASP and other groups that are involved in this area. So now let's talk about some control strategies. So renewables can provide oscillation damping services if they are controlled in a proper way. So basically, if your wind and solar, any IBR is pre-curtailed, as shown on a graph on the left, you can modulate the output within an available headroom to provide the oscillations. But this has economic implications because curtailment costs money. You don't want to keep your devices curtailed all the time just to provide this service. Also, accurate determination of that headroom is also not an exact science. By the time you need to provide it, it may not be available because once you curtail, you lose accurate information about that headroom. So one possible way of doing it is to do this so-called half sine wave damping. When device is not curtailed, when the oscillation is needed, it provides its output, only half portion of a sine wave. We'll show results to show that it's possible, but it's economic way because you don't have to pre-curtail, and only have to make sure that the fundamental harmonic of this response has a phase and amplitude that you need to damp, and you have to make sure that other harmonics may exist that are not causing you problem. And another way of doing it on the bottom graph is you are not pre-curtailed, but as soon as you detect the oscillations, then you curtail, provide damping service, and go back. So the methods 2 and 3 are essentially energy free, because you don't have pre-curtailment, and it's a very short period of time you provide that service that you need to curtail. So there is no real financial loss for the plant owners, but it provides significant benefit to the grid. So going now quickly for different cases, that two-area system I demonstrated. So the result of a test, when nobody is provided damping, the system goes out of stability right away. Everything trips off in that PHL setup, so we have to start the experiment all over. This is an example of the interior oscillations triggered again by a change in the power balance. And you can see that with this wide area control and 300 millisecond delay with the proper compensation, the damping is being provided and system is stable. So in here, we also have a AGC scheme that eventually will bring the frequency back into a normal in both areas. And this is an example when we have much longer delay, about 900 milliseconds. You still can provide damping, it takes longer time. This was kind of a limit of the time delay that we were able to achieve a stable recovery or stable performance of a system. Doesn't mean that longer periods are not possible, just with a particular setup and with the particular communication scheme we have, that's what we achieve. 3 more minutes? Yeah. Okay. And also, if you lose a communication, one area damping is possible. So with an example when damping is provided only with a IBR on one part of a system, which is a battery energy storage system. Of course, it takes longer recovery time. This is a case with a local damping control that can be faster as well under certain conditions. But the local damping control works well in this case, but when you have a larger system with many devices trying to do things in an uncoordinated way, this may be actually stability deteriorator. And then there is a case when I was talking about when there is no pre-curtailment event happens and both PV and battery storage modulate their power down, damp the oscillation, and then the system comes back into the normal state. So there's a very promising thing showing that you can achieve this type of service without pre-curtailment. System can also be disturbed by the large voltage transients. When we introduce the voltage fault in the system, that is also introduced on the buses that both renewable systems are seeing. And we also tried a different type of recovery scheme with a different relays, and the system recovers nice, like shown in this graph. And one of the last tests is the when we are using the grid forming controls by renewable. In this particular case is a grid forming type 3 wind turbine. And to our surprise, we found that just the mere presence of a grid forming resource in that scheme changes the overall damping characteristics of a system. So there is more damping in the system, so the recovery is much easier. So this is a case when we have grid forming wind on one side and the PV on the other side. But then even if PV doesn't do anything, that grid forming wind is enough to provide damping in the system. Type 3 wind turbines have significant advantages compared to other turbines. I'm sorry, it has a significant advantage in the grid forming mode because we showed in our previous research that it has a high levels of short circuit current, which is beneficial to the system, but more importantly, it is immune to subsynchronous resonances because it changes again the damping characteristics of a type 3 wind power plant. Synchronous condensers can also be a very useful resource. In fact, synchronous condensers are used for oscillations damping already in the UK in a national grid. This is an example of the ABB system deployed in a national grid. We are in touch with ABB and doing the similar type of things with the synchronous condenser we have at NREL, doing some testing and characterizing. This is an example of a frequency response test for that synchronous condenser when its excitation is controlled in a sine with a sine wave controls, and we're trying to see the response of a system. So the inertia of a synchronous condenser is the important thing, but more importantly, when you control the synchronous condenser and excite it or oscillate its reactive power, you also change the active power flow in the system. So if you do it in a correct way, it can also become a damping factor. And last is the subsynchronous resonance case where we took IEEE subsynchronous resonance test case, and we used the battery storage to damp this subsynchronous resonance. On the left side, as there is no damping, so the system goes out totally unstable. And on the right side, the battery provides damping control. So the zoomed in response over battery. Our testing shows that batteries can respond within 20 to 30 milliseconds, which is roughly 50 hertz bandwidth. that makes them suitable for damping oscillations down to 20 hertz and below. So as a summary, in next steps, we'll continue research in this area, despite the fact we demonstrated a lot of things, but this is an ongoing work. We're dealing with the hardware, things are delayed, things don't work in a way you want, so we have to do things over and over. But nevertheless, there is a significant progress. We need to understand better what are the advantages and disadvantages of a local versus centralized control, which one is better in the different levels of penetration, and also the maybe hybrid controls also are needed to be considered for a system. So we'll continue with demonstration of stability services. We'll also be looking at the role of grid forming resources, high voltage DC, especially in the context of offshore wind, and so forth. So that's a summary of our work. I apologize, I went over time, but
That's fine. Thanks,
that's it.
Vahan.
Yeah.
Thank you.